presentation, we will address what RL circuits are, using ODEs to solve for the generalized equation, and applications of the equation. First, we will outline what is an RL circuit. An RL circuit contains an inductor connected in series with a resistor. The resistance R is a resistive value of the wire turns or loops that goes into making up the inductor's coil. Next, we will address what a variable separable equation is. A variable separable equation is any differential equation that we can write in the following form. To solve a variable separable differential equation, we separate all the values of x and y to opposite sides of the equation so that we have dy over the y's and the x values times dx. Then we integrate both sides to get rid of the derivative.
To solve for the generalized equation, we can analyze the circuit on the right. The circuit has a power supply connected in series with a switch, a resistor, and an inductor. Notice that time equals 0. The switch is open and hence no current can flow through the circuit. This becomes important later. Firstly, we'll set up our equations. Ohm's law states that V equals IR and that the voltage across the inductor is equal to V equals L di dt. Kirchhoff's voltage law states that the algebraic sum of the voltage drops around a closed loop is 0. Hence we can say that R plus L di dt equals V. Once the switch is closed, the current in the circuit is not constant. Instead, it will increase from 0 until it reaches a steady state. To determine how the current changes with reference to time, we must solve the differential equation R plus L di dt equals V. By rearranging, we obtain di dt equals V minus Ri on L. This is a variable separable equation. As Jacob explained earlier, it can be separated into its two variables and then both sides can be integrated. By integrating both sides, we get where k is a constant of integration. Now, since initial conditions are that I equals 0 when t equals 0, we have k equals negative ln of v on r. Then we can substitute k back into the expression and rearrange to get this. Then, by multiplying by negative r and collecting the logarithm parts together, we get ln of v minus ri on v equals rl on t. Taking the exponential to both sides gives I minus ri on v equals e to the negative rl on t. Finally, to get the equation in the right form, we can subtract 1 from each side, then multiply each side by negative v on r. By doing this, we obtain the generalized formula I equals v on r, 1 minus e to the negative rl on t. So to recap, this formula was derived from the use of differential equations and has many uses in electrical engineering applications, which Jurra will explain.
One of these uses in electrical engineering is through the use of transformers. A transformer utilizes Faraday's law and the ferromagnetic properties of an iron core to influence AC voltage. As seen in the diagram, the transformer contains a voltage source, a resistor, and two coils around the iron core. These coils act as an inductor in this system, therefore completing the RL circuit. Transformers can be used in a number of electronic devices. It is the transformer's job to supply the device with as much power as it requires to function. Voltage can be lost or gained depending on the number of coils the inductor on each side has. That is, if the number of coils on the primary side is greater than the number of coils on the secondary side, then the voltage on the primary side is greater than the voltage on the secondary side, and vice versa. To name a few examples of household products that use a transformer include laptops, phone chargers, washing machines, and dishwashers.